When you open a web browser, the software operates without knowing how its data will physically travel. It generates a request, whether the connection relies on a buried fiber optic cable, a copper Ethernet line, or a wireless radio wave. Facilitating communication across millions of disparate hardware and software configurations requires a modular system of abstraction. This abstraction allows a developer to write a single application that functions seamlessly across every conceivable physical medium. This abstraction is enforced through encapsulation. It is the sequential process of taking data and wrapping it in layer-specific control headers. As data moves down the network stack, each layer concatenates its own instructions, preparing the data for the layer below. In technical terms, the raw data handed down from an upper layer is the service data unit, or SDU. Once a layer attaches its own header to that SDU, the combined package becomes a protocol data unit, or PDU. We will reconstruct the byte-level mechanics, see how VPNs utilize these rules, and examine the persistent connectivity hangs that occur when protocol overhead exceeds hardware capacity. The internet scales because each layer treats the data it receives from above as an opaque, untouchable payload. In this modular architecture, a protocol only communicates with its direct counterpart on the receiving machine. Application data enters the transport layer. Because TCP cannot send infinite data, it divides the stream into manageable segments. It attaches a 20-byte TCP header to enable multiplexing, allowing multiple applications to share one connection simultaneously. Inside, 16-bit source and destination port numbers act as internal addresses, routing incoming data to the correct software process, like port 443 for web traffic. The header contains sequence numbers to ensure the payload is reassembled in order, and control flags like SYN and ACK to manage the connection state. By the end of Layer 4 processing, a raw data stream has been converted into structured, reliable conversations between specific applications. The transport layer hands the segment to the network layer, treating it as a single SDU payload. Layer 3 wraps this payload inside an IP packet, appending an IPv4 header standardized in RFC 791. This header contains 32-bit source and destination IP addresses, acting as shipping labels with logical addressing, so routers can determine the path across independent networks. The header also includes an 8-bit protocol field. A value of 6 in this field identifies the encapsulated payload as TCP. These instructions tell the receiving machine's network layer which transport protocol must receive the data after decapsulation. Layer 3 allows data to traverse global networks based on logical addresses, regardless of the physical medium of any intermediary hop. To reach a local gateway, the IP packet must be prepared for a specific physical segment by Layer 2, the data link layer. Ethernet encapsulation is unique because it appends both a header and a trailer, converting the IP packet into a frame. The Ethernet header uses 48-bit media access control addresses to target specific hardware on the local network. Modern networks use two framing standards. In Ethernet 2, the 2-byte field following the source MAC is an ether type, identifying the upper layer protocol. In the formal IEEE 802.3 standard, that same 2-byte field is used instead to identify the payload length. At the end of the frame is the frame check sequence trailer. The sender performs a cyclic redundancy check and stores the 4-byte result here. When the hardware receives this frame, it runs the same calculation. If the results do not match the trailer, the frame is considered corrupt and is dropped before it reaches the upper layers. Layer 2 ensures structural integrity before the PDU is converted into raw bits for transmission across the physical medium at Layer 1. Standard encapsulation delivers data, but doesn't hide the path. Securing data over public infrastructure requires a modification of these rules through tunneling. Tunneling is recursive encapsulation, the process of wrapping a passenger protocol entirely inside a carrier protocol. The IPSec suite utilizes the Encapsulating Security Payload, or ESP. In transport mode, the system encrypts only the payload, leaving the original IP header visible to anyone monitoring the traffic. In tunnel mode, the entire original IP packet is encrypted into an unreadable block, protected by an ESP header and trailer. To route this encrypted block, the system appends a new, unencrypted outer carrier header. This directs the traffic to a VPN gateway. Intermediary ISPs see only the carrier traffic. The original source, final destination, and internal payload remain hidden within the encrypted tunnel. By utilizing the existing encapsulation hierarchy, VPNs create a mathematical layer of camouflage that routes data through public space without exposing its content. While software can stack these headers recursively, the underlying hardware at the data link layer has a fixed capacity. This capacity is the maximum transmission unit, or MTU. It is the largest frame size a network link can transmit. Standard Ethernet is limited to 1500 bytes. If an application generates a 1500 byte packet and routes it through a VPN, the 70 bytes of ESP overhead create a 1570 byte packet. When that packet hits an interface with a 1500 byte limit, it cannot pass. The router breaks the packet into fragments. This initiates IPv4 fragmentation, as defined in RFC 791. The router splits the payload and replicates the IP header for each resulting piece. Fragmentation ensures delivery, but it increases CPU usage on the router and consumes more bandwidth. If a single fragment is lost, the entire original datagram is discarded. To prevent fragmentation, networks use Path MTU discovery. This mechanism probes a route to identify the lowest MTU bottleneck before full data transmission. This process relies on routers dropping oversized packets and sending back an ICMP fragmentation needed message. However, if a firewall blocks these ICMP messages, the sending host never receives the warning. This results in a black hole router. Small requests, such as a login, may succeed, but larger data transfers will time out and hang indefinitely. ALS diagnose these issues using utilities like tracepath or pings with the don't fragment bet enforced. If a ping at 1472 bytes fails, but a smaller one succeeds, the MTU bottleneck is identified. To resolve this in VPN environments, routers can be configured for MSS clamping. This forces the endpoints to negotiate a smaller maximum segment size during the initial TCP handshake, leaving room for the encapsulation headers. Building a functional network requires aligning the logical layers of the network model with the physical limitations of the hardware. Understanding where these two systems meet is the final step in ensuring reliable data delivery.